Swayam Prabha. Digital India. Educated India.
So in the remaining class that we have right now, what I want to do is the first application of network flows to something that you have already seen, which is computing matchings in bipartite graphs. So let me recall, we have a bipartite graph, we have certain edges in that bipartite graph, and we call a collection of edges a matching if no two edges share an endpoint, right. So these red edges form a matching in this bipartite graph, and we are interested in computing a maximum matching, that is a matching which has largest number of edges and which still satisfies the property that it continues to be a matching in any bipartite graph, right. So we have seen some structural properties. We have also seen when is a matching a maximum matching. So can somebody recall when will be a matching a maximum matching? You must have seen some theorem for this. Okay, think about it. It's related to matchings, but it is not the condition when it is a maximum matching. So if what you are saying is, if you take any subset of vertices on the AX, I think this was called as an XY bipartite graph, right? So then any subset of the vertices on the X side should have a neighborhood which is as large as this, right? This is what you are saying for the matching to be maximum. Okay, that is when would you have a perfect matching, right? But every graph need not have a perfect matching. So my question is, this graph, is this red matching a maximum matching, or can you find me a matching which has size 3? Why is this a maximum matching? Augmenting path, very good. So you know that there is a characterization of matchings which says that a matching is maximum if and only if there is no augmenting path with respect to it, right. So now we are going to see whether we can actually use that idea and get an algorithm to compute a maximum matching in a bipartite graph, right. So have you seen an algorithm to compute a maximum matching? In the lecture that you have you seen an algorithm? How do you actually compute a maximum matching? You have seen a characterization, that is, if the matching is maximum, there is no augmenting path. If the matching has an augmenting path, you will be able to increase the size of the matching. So we want to convert these ideas into an algorithmic procedure, and now what we are going to do is not invent algorithms newly. We are going to say that, can I convert this question into a network flow question where I just say that give me a max flow in that network, and then that itself will tell us what is the maximum matching in that graph that we want. Now this seems to be slightly far-fetched, because bipartite matchings are just asking you compute some things which are a subset of edges, and flows are a different quantity where it's a function that we want to compute on the edge, say, right. So this procedure is actually called as a reduction. So what we are going to do is bipartite matchings to network flows. So let me state the idea of a reduction first. So what is a reduction? A reduction is that you have a problem X, you do not know how to solve that problem. So think of the problem X being, as school kids, when we are not taught multiplication, we do not know how to multiply two numbers. We can convert the problem of multiplication into a simpler problem that we know. So what is the problem? That is addition, right. So if I am given to multiply two numbers A and B, I can repeatedly add A B many times or B A many times to get the multiplied sum. So if one sees this is a non-trivial idea actually, that you should take a problem X and convert it into an instance of problem Y, such that the solution to this problem, solution to the instance of problem Y is just going to quite immediately give you the answer to the problem X. So in this case what you will do is A plus A plus A b times, this is one way to reduce it, or b plus b plus b a times. Both these are correct ways, and whichever you solve correctly for the problem y is going to give you an answer to problem x, right? And what does this, as computer engineers as well, what does it allow us to do? If I had written a correct tested routine for problem y, and if I do this procedure correctly, that is, I should not make any mistakes here, I should not give add a b minus 1 times, then the answer is still going to be incorrect how much ever correctly you have implemented addition. But if I do two things correctly, one is I do this reduction correctly, the second is I have implemented faithfully the solution for problem y, then I will be guaranteed that this problem x is solved correctly. So now what we will assume is that network flows, somebody has implemented a routine for us or implemented algorithms for us which will give us the correct maximum flow in any flow network. We would like to establish this reduction and prove the correctness of the reduction. So here it is very trivial, there is nothing to prove, almost to say that a into b is equal to a added b times or b added a times, but in this context when we are going to talk about, we will have to establish the correctness of the reduction, right? So we'll attempt our first reduction now, and I am going to start with some hints, right? So first, and we are going to, hopefully you are going to help me build this flow network. So what is it that is completely distinct between these? One, this is an undirected graph. We should come up with a directed graph first, right? If we wanted a flow network, we should also have, so we should come up with a directed graph. We should have capacities associated with edges, and we should have designated vertices S and T. We should certainly have this to even talk about a flow network, right? So I am going to set up the directed graph, I am also going to set up S and T. You are going to tell me what are the capacities, right? So I will keep the internal structure of the bipartite graph as it is, but all the edges from x to y, I am going to direct, I mean from between x and y, I am going to direct from x to y. So I will take this example and I will construct the flow network. And now what I am going to do is, so till here I have at least gone to a directed graph from an undirected graph. I am going to add two dummy vertices S and T. I am allowed to change my networks as long as I do some polynomial amount of time. In fact, one can do even larger, but here I am doing only constant amount of addition. Okay, this is my flow network. So I have completely described the flow network except for the capacities as I promised. So what I have done is, I have taken all the edges in the bipartite graph, directed them from one side to the other, right? Choose any side, but choose that for once, direct them from one side to the other, and then add add two vertices S and T, and from S to every other vertex in X, you add a directed edge. For every other vertex in T, every vertex in Y, you add an edge from that vertex to T, directed edge. Now what are guesses for capacities of these edges? Maybe I will just start with 1, right? Okay, I will give a capacity of 1 for all these edges. So this is the suggestion, I will not write everywhere, but all the edges are unit capacity. So let us first ask, what can be the value of the max flow in such a network, right? Now let us make, so in this network maybe you can even tell what is the value of the max flow, but I will make it slightly general. So you have a bipartite graph with x number of vertices, cardinality of x number of vertices and cardinality of y number of vertices. Can you say that the max flow value in such a network that you have constructed is at most this number? Okay, so what he is suggesting is that the value of the flow is at most the number of vertices into number of vertices in X into the capacity, but the capacity we have chosen as unit, right? So therefore it is it is exactly equal to the cardinality of x is what you are saying. I am claiming that you can refine it a little bit. Whenever we want an upper bound, we want an upper bound which is as small as possible, because if I say that the max flow is going to be less than or equal to x into y, it is going to be a trivial, I mean it is going to be a non-useful upper bound. Upper bound of x, that is cardinality of x, is much better than some arbitrary upper bound as x into y. But now what is a better upper bound than this? Yeah, y is in this example, but in general it would be minimum of x and y. Very good, right? So clearly that the max flow is upper bounded by this value. You need not have a max flow of this achieving this value, but if you have, then you will again show an optimal cut which validates or shows that your max flow value is optimal, right? Okay, so what do we do now? Once we have constructed this flow network, we subject it to a flow algorithm. Ford-Fulkerson or any other algorithm which is efficient, we just subject it to that flow algorithm, and then we get a max flow in this flow network. Now we would like to ask, what is the relationship between the value of the max flow and the value of the maximum matching in the graph G that we had, and then we should ask what are the actual edges belonging to the maximum matching. These are the two questions, because we want to retrieve a maximum matching. So let us do one direction first. So I will call this bipartite graph as G, the flow network as D, as we had called in the morning, right? So the first claim is that if G has a matching of size K, then D has a flow of value K. Remember, I have never said that it has a maximum matching of size K. It just says that if you show me some matching of size K, I will be able to exhibit a flow value of a flow whose value is exactly equal to K. So is this simple enough given the way we have set up our flow network? So suppose in general you have a maximum suppose you have a matching of size K, that means you must have these disjoint edges where K many edges are present in the bipartite graph G. How can you show me a flow function which is a valid flow function in the graph D and also has a value of K, right? So remember that if the edges were like this, they must have been directed from x to y in the corresponding flow network, right? But those are not the only edges, we have added some more edges. So you should show me valid ST flow function which has a value which is equal to K. So how would you construct that flow function? Flow along all these edges in the corresponding directed network is exactly equal to 1. But is that okay? Is that sufficient? So what you are saying is you just send a 1 over 1 here, right? These were my edges, sorry, not here, here, right? This is what you are saying. But I claim that this is not a valid flow function, right? Okay, so let me name these. So this is A1, A2, A3. So can you explicitly say, so I must give from S to A2 1 unit of flow, right? S to A1 1 unit of flow. Similarly, I should give from whatever B1 to T 1 unit of flow and B2 to T 1 unit of flow. Rest 0, right? So what is your general formula? If you have an edge little x1 y1 which is belonging to the matching in the graph G, you take the edge S x1 is equal to, so I will just write this, f of S x1 is equal to f of x1 y1 is equal to f of y1 t, which is equal to 1. For every edge x1 y1 which belongs to the matching, you are simply going to set the flow values on all the 3 edges as 1. It is clear that it satisfies the capacity constraint because you had set the capacities to be equal to 1. What about the flow conservation? In fact, the flow conservation is very easy because in this graph, bipartite graph, because you have picked up edges of the matching, no two vertices will have 2 edges incident on it. Therefore, every edge will have exactly one incoming edge here from S, and every vertex which has non-zero flow outgoing from it on the x side will have exactly one incoming edge which has 1 unit of flow, and every vertex y which has an outgoing an incoming flow will have again one outgoing edge. Right? Therefore, flow conservation is again maintained. So, therefore, what does this show us? That you take any matching in this graph and I will be able to construct a corresponding flow which has value exactly equal to the value of the matching. Why is the value exactly equal? Because again, if you see, there are no incoming edges to S, there are only outgoing edges from S, and how many outgoing edges have 1 unit of flow? Exactly k many, which correspond to the edges belonging to the matching, right? So, therefore, this shows that if G has a maximum matching of size k, then D has a flow value of k. That is all it shows, because again there may be, so it says that if you give me any matching of a particular value, I will construct a flow of the same value. Therefore, the max flow in D has value greater than or equal to the max matching in G. So, if you wanted to show two quantities are equal, it is very easy to show that one of them is greater than the other and the other is greater than the first, and if you show both of these inequalities, then you get that they are equal, right? And this is exactly what we are trying to do. Okay. So, what is the remaining part? If I give you any flow in this network, you must be able to convert it into a matching of the same value. So, whatever is the value of the flow, you are going to convert it into the same, convert it into a matching of the same size, right? So, again, what is the natural procedure? So, I have subjected this flow network to a max flow algorithm. It has computed some, actually not even max flow, any flow it has computed. If you compute any flow, I should be able to convert it into some matching. Therefore, a max flow will also be converted into some matching. Again, it will say that the value of the max matching is greater than or equal to the value of the max flow, establishing the equality. So, what he is saying is, you only concentrate on the internal graph, which is the actual bipartite graph. Look at the edges in the internal bipartite graph, which now have become directed, but whichever edges carry flow, retain them, and your claim is that that will correspond to a matching. So, this is what we want to prove, because a flow network does not guarantee that in general, but the way you have constructed the flow network, it should guarantee that, right. So, now what we are trying to show is, you take the bipartite graph that, so you take the graph D, concentrate only on the bipartite graph, look at edges that maybe got unit flow. These are the only edges that got unit flow, let us say, and because I want to establish a I want to prove it, I am saying for the sake of contradiction, it happens that there are two edges incident on a vertex which gets 1 unit of flow, right, because if everything, every vertex has at most one edge incident, then it is a matching, and because it and again we need to argue that it is of the same value, but let us first argue that it happens to be a matching. Why should such a condition not happen? That a vertex on the B side will have Y side will have actually two edges incident on it which carry unit flow in the max flow. Very good. So, here we had given a flow, we had given a edge from whatever y1 to t, which had capacity exactly 1, and therefore flow must be conserved at this vertex. For that, you cannot send 2 units of flow incoming to y. A similar argument will show that you cannot have 2 edges outgoing from S, because any vertex on the x side has exactly 1 unit of flow incoming to it from S, right. So, it is a matching. Now, what about the value of the matching? Value of the flow is exactly equal to the, so you have found out exactly equal number of edges equal to the value of the flow. Again, that is not true in a general flow network. So in a particular flow network, maybe the value of the flow is 10 units, but you have exactly one edge in such a bipartite graph if the capacities were different. But here the argument is simple because you have unit capacity edges, so no edge can carry more than 1 unit of flow. So if you have a flow value which is k units, then you must have k distinct edges which are contributing to the flow, right? And therefore you have exactly computed a matching of the same size as the value of the flow, and establishing that these two quantities are indeed equal. That is, the value of the max flow in D is exactly equal to the maximum matching in G, right? So this is a reduction that establishes that if you have a bipartite graph where you want to compute a matching, you could just invoke the network flow algorithm on a suitably modified graph. So let us analyze the running time of our Ford-Fulkerson method on this modified flow network, right? And we have already done much of the analysis so that we can just plug in values now, right? So we said that the Ford-Fulkerson method runs in time, which is value of f star into m plus n, right? M is the number of edges in the bipartite graph, n is the number of, actually not edges in the bipartite graph, m is the number of edges in the flow network, n is the number of vertices in the flow network, and we should relate all of these back to the bipartite graph, right? So to make the distinction clear, we will say that G has GVE, which is a bipartite graph, has V equal to N, E equal to M, and we need to compute what is the, so we will call this V prime E prime. We need to ask what is the size of V prime in terms of V. That is, how many vertices do we have? That is simple. We have V prime, the cardinality of V prime is just V plus 2 because we have added 2 vertices. What about the cardinality of E prime? It certainly has all the edges in the original graph plus some additional edges, plus V, because exactly one edge we have added extra, so we will just add a V here. So we have not increased the size of the graph too much. And then what is the value of the max flow? So we agreed that the value of the maximum matching or a value of the max flow in such a network is always upper bounded by min of the values, the cardinalities of x and y. So in fact one can upper bound the value of the max flow to be by V, that is the number of edges, which is slightly weaker, but this is V, which is the number of edges in this, the number of vertices in this original graph. So V into cardinality of V plus 2 plus cardinality of E plus V, the overall term happens to be V plus V times V plus E. I mean, we will hide all this in the order notation, right? So the running time of the algorithm for computing bipartite matchings is just, so this is simply written as V times E or Mn, right? That is the running time of the algorithm. Remember that this E is the edges in the edges in the original bipartite graph, and V is the number of edges in the V is the number of vertices in the original bipartite graph. So what we get is a polynomial time algorithm using the simple Ford-Fulkerson technique template to compute maximum matchings in the bipartite graph.